Well, actually, before I wanted to start, I was hoping the organizer is around, but I don't know where he went. Maybe we can thank him after the talk. Okay. Well, with that, let me actually start with my talk. Yeah, today it's the end of the conference. I'm tired, I know, and so I thought I'm going to give you a little bit of a lighter overview about some of the recent developments in what are called detector event shapes, and I'll explain what those things are. And I'll give you kind of a bird's eye view ranging from particle colliders all the way to classical and then quantum gravity. So what I'm going to talk about is work with Ian Moult and Murat Kuloglu at Yale, and then also some work in progress together with Kai Yan. Okay, so I start with a little bit of broader motivation. So this is going to take quite a bit of time. And then I go through some of the things in a little more detail. I'll tell you about event shapes in quantum field theory, and in particular for collider experiments. There I'll be a little bit brief because Washing yesterday or 2 days ago already gave a nice talk in this direction. And then I'll explain how LIGO and gravitational wave detectors can be understood in this new language of event shapes and detectors. And then I'll come to a kind of more inspirational field that's trying to study these event shapes in quantum gravity and trying to make sense of quantum gravity in this terms of like asymptotic measurements. And then I'll close with some future directions. So we can go to a poll or go out to the street and ask people, what's a detector? And I think in this room, some people might answer, well, a detector is either ATLAS or CMS at a particle collider at the LHC. Or maybe 40% of the audience here would say, oh, a detector has to do with gravitational waves. Well, maybe soon we only have one. We'll see what happens. It's not so much to laugh, but well, we'll see what happens. So this is the gravitational wave detectors of LIGO. So this is from an experimental site, what we could think of as a detector. So, but in recent years, there's been an increased understanding of how we should think about these detectors in the language of quantum field theory. And that goes back to some work, like, well, amongst other people, with Simon Caron-Huot, David Simmons-Duffins, and others, in quantum field theory, in particular conformal field theory. So we're pretty familiar with the sense that we can probe a physical system in terms of local operators. So they have this very nice picture of hammers and cameras. So from condensed matter physics or many other contexts, we're kind of familiar with this picture of a hammer. So we can test and excite and probe a system with local operators, and then we can study its dynamics by measuring correlation functions of local operators. But in the last couple of years, there's been kind of a complementary picture evolving, where instead of studying systems or the dynamics of systems in terms of correlation functions of local operators, we should think about trying to characterize the physics of a system or its dynamics in terms of doing asymptotic measurements. So this is something that we're very familiar with colliders. We do kind of asymptotic cross-section type measurements. And so there has been a framework developed of how we are supposed to formulate these detectors in quantum field theory. And this goes under the name of light ray operators. Instead of the local operators that we're very familiar with, these light ray operators are not local. They're supported on null lines. And so why is this picture useful? It's useful for many things, but for me, it's also an interesting framework because I'm ultimately also interested in quantum gravity. And famously in quantum gravity, we do not have local degrees of freedom, or local operators are not meaningful because spacetime itself is fluctuating. So in quantum gravity, we should only kind of consider these types of asymptotic observables. So maybe my suggestion is that maybe for quantum gravity, we should only study, or this framework of light ray operators and detector operators is useful to say something interesting about quantum gravity. So this is kind of a highfalutin goal. I will not I'll not solve this problem in generality, but I make some initial steps in these directions. So we've already seen from Washing, so this is actually stolen from Washing's and David Simmons-Duffins' paper, that these light ray operators are useful in the sense that they provide natural analytic continuations in spin of local operators. And they kind of organize the spectrum of your theory in these terms of Regge trajectories. So in free theories, you just have these straight line trajectories, maybe some horizontal trajectories. Washing talked about a lot in a lot of detail of these trajectories in QCD. And interestingly, like you're familiar with local operators, that once you turn on interactions, local operators can get renormalized. There's operator mixing, and so on and so forth. We heard about some of these things in the course of this conference. These detector operators can also mix and get renormalized. And so in that sense, yeah, there's very much an analogy to what you're familiar with from local operators to these light ray operators. Yeah. So one more kind of on the formal side, another nice thing, also an analogy to the local operator case, it's that there's this algebra of detectors that you can talk about. And here today, I just want to say about one thing that you can take, like you're familiar with the operator product expansion, Euclidean operator product expansion of local operators. These light ray operators satisfy kind of a Lorentzian version of this operator product expansion called light ray operator product expansion, where you can take two of these light ray operators, you can bring them together, and they allow you to form new operators. So that's something interesting. So you can take two operators that you know in your theory, you can try to bring them together and study, like maybe you can detect like new types of detectors that you can then study independently. And furthermore, like for certain observables, the nice thing is this in this operator product expansion limit, it dictates certain scaling behaviors of observables. So now in this like more modern framework, it's like human-made observables can then be expressed in terms of correlation functions, or what are called event shapes. That's in my title, event shapes of these detector operators. And the nice thing is, well, there's a nice theoretical structure behind these detector operators and event shapes, but we also have experiments where you can directly measure them. So that's, for me, it's a very exciting feature. So this was a bit abstract, and yeah, so we can define them in more generality. So there's a whole structure, theoretical structure underlying them. But so maybe we want to be a little more concrete. And so today I want to mainly focus on what one could call energy correlators. And in particular, the detector associated to them are called energy flow operators, or ANIC. So which is given as in terms of the stress tensor of your theory. And basically this thing is a calorimeter cell which measures energy flux at asymptotic infinity in some particular direction that's given by some vector, some normal vector n. And then you put these detectors at asymptotic infinity, you take a limit of r goes to infinity. So that you have to do in a general QFT. In CFT, you can just do a conformal map and map them to infinity straight away. So this energy flow operator is very interesting from many perspectives. That has been used to prove like C theorems, that there's a connection to quantum information and so on and so forth. But it's also the most well-studied detector operator in the collider settings and stuff like this. So I will focus on this mainly. So once we have our detector, we can ask for correlation functions of multiple of these detectors in some particular state. So crucially, like once these non-local operators act on the vacuum, they annihilate the vacuum. So you need to measure them to get something non-zero. You need to measure them in some non-trivial state psi. So there's two kind of complementary perspectives on these event shapes. One is more, I would call kind of the CFT type framework, where you really view them as correlation functions in correlation functions. But here we are at the Amplitudes conference, so there's kind of a complementary point of view. You can insert in cases where you have asymptotic one single particle states, you can insert a complete set of states in the asymptotic future and relate them to differential cross sections. And then you can just use their action on these single particle states that for the energy operator here, it just weights the particle by its energy. And then you can express these in correlation functions in terms of some weighted cross sections in terms of scattering amplitudes. So that's why I'm telling you about these things here at the Amplitudes conference. So just to summarize a bit of what we've seen here, it's I started with kind of a more formal motivation. We have this new language of like phrasing detectors and quantum field theory. So there's a nice like formal aspect of like studying these interesting objects. But they, as we'll see, as I'll show in a little bit, that there is a nice connection between some of these formal aspects of these detectors and like actual particle physics measurements. There's actually like you can also try to measure them at finite density and finite temperature, and relevant for nuclear physics. And also, what I'm going to talk about also is you can view LIGO in terms of these event shape in this event shape framework in classical general relativity and GR. So from the phenomenological side, is you might want to measure some of these event shapes at colliders to study the dynamics of your theory. And then the nice thing is for some of these event shapes, you can have very precise theoretical predictions, and then you can compare experiments to precision theory. So from the more formal side, and that's also what I'm mostly aiming for the gravitational aspects or for the quantum gravity aspect, is you can try to explore the space of asymptotic observables in your quantum field theory. And it seems that this asymptotic measurement setup is kind of the natural or suitable framework for quantum gravity. So let me start with the first part, these event shapes at colliders and in quantum field theory. So there's a long list of people who've been working on this. I certainly have not listed everyone, and I apologize for people who got it omitted. But so these energy correlators and these event shapes in terms of this ANIC operator, they're actually not very new. They're very old, in fact. So they're like 50 years old. They were first discussed by Sturman in 1975, and then generalizations to higher point by Ellis and collaborators a few years later. And like Lance and many other people here in this room have also already worked on this. So we can try to measure these event shapes at colliders, and Huaxing also already said something about this. So I would be remiss to advertise. So if you're interested in these types of ideas, I highly recommend this very recent review article by Ian Mould and Huaxing on energy correlators that give like much more information about many of the physical things and like computational things that go into these event shapes. So I highly recommend their very recent review article if you're interested in these types of physics. So let me discuss a bit the energy correlators in an initial state that's generated by a local source or by a local operator. So this is kind of this is standard, or like one of the initial setups by Hoffman and Maltasena, and it's also like conceptually the easiest thing. You generate some initial state by acting with some local operator O on the vacuum that generates some excitation, and that excitation propagates out to asymptotic infinity. And then you have your detector operators at positions N1 and N2 located at the celestial sphere. So this is, again, this kind of complementary picture. You can either think of this in terms of the correlation function or in terms of weighted cross-section. So you have a differential cross-section. It's like the form factor of this local operator squared, weighted by the energy of the two particles that you measure at asymptotic infinity. And then it depends, like in this variant of the energy correlator that I'm describing here, this observable depends on the opening angle between these two detectors. And then you can ask differentially in this opening angle of how this observable behaves. So this is actually, it seems like a simple observable, but even as I will show in the next slide, even for this relatively simple observable, it shows insanely rich physics. So it's a rich physics that's sensitive to the dynamics of the theory. And one nice thing about this observable is that we have very good perturbative control, where we know things to next to leading order analytically in QCD, to next to leading order in QCD, we know things numerically. And then in n equals 4 super Yang Mills, we even have next to leading order analytic results. So these things are nice from a theory side. We have theoretical control, perturbative control, but we can also measure these things in E plus E minus collisions. Where in E plus E minus collision, so you just generate a state by the electromagnetic current. So this event shape is actually quite intricate, and like this slide is very busy. I just want you to take away here a few key things. So what you see here on the x-axis is basically a plot of the opening angle between these two detectors. So I converted the angle to some more conventional variable that I call z. And on the left-hand side of this plot, this is the small angle limit, which means that the two detectors are very collinear. On the other hand, it's the limit of like the angle equals pi. That means the detectors are back to back. And so one nice thing with this observable is that you can actually probe almost like in a renormalization group flow of this, in the sense that if you have hard scattering at finite angles, you have some hard scale q squared of like the off-shellness or the virtuality of your photon. So you have a hard scale, and here you can use really perturbation theory due to asymptotic freedom. You can have like the strong coupling is weak at high energies, so you can do perturbative extensions. But then you have this kinematic variable. You have this opening angle, and you can use this angle to basically tune your renormalization group scale, in the sense that the relevant scale at particular angles, especially if you tune either to very small angles or to angles close to pi, is not the virtuality itself, but z times this virtuality. And so by tuning to smaller and smaller angles, you can effectively probe scales that approach lambda QCD. So you have access in this observable from both perturbative regime to perturbation theory. And there's a lot more interesting physics that happens in this plot that I will not have time to discuss about. But yeah, so one nice thing is here at this turnover point, this is really where confinement transition happens. So you have access in this observable to kind of the confinement transition. And the nice thing is there's a lot of like actually data. There's a bunch of data that you can match your theory predictions onto. So all of this data is mostly from the 80s and 90s. Yeah, so some old E plus E minus data. But also for charged particles, there's a recent reanalysis of experimental data that allow you to make more predictions. So yeah, so this is a very interesting, so it's a very interesting observable where you have both from perturbation theory to resummation to non-perturbative effects. So, okay, this was my Blitz version of E plus E of energy correlators and colliders. So now I want to go from QCD to gravity, switch tacks a little bit. And first I want to explain to you that we can understand the LIGO experiment gravitational wave detectors in kind of the same language. Namely that our LIGO detectors, they're sitting asymptotically far away from where these two black holes are inspiraling or colliding or whatever. They're emitting gravitational radiation that we're detecting with our detectors asymptotically far away. So in that sense, just like colliders measured event shapes, we can also say LIGO measures event shapes. So we've heard in this conference multiple talks on how we can use scattering amplitudes tools to make predictions for classical two-body problems. And so kind of the underlying reason why this is working is due to effective field theory and the quantum field theorist's point of view on this black hole or classical black hole inspiral or scattering problems is that we can take our lens of EFT, we can now take our zoom. Once we zoom very far out from the black hole, we can treat them as effective point particles. And thanks to the no-hair theorem, black holes are characterized by very few quantum numbers: mass, electric charge, and angular momentum. So in the simplest case, we can describe Schwarzschild, like non-spinning, non-charged black holes in terms of massive scalar fields in our quantum field theory setup. So, and there's been many tools developed to how we can extract classical observables from quantum scattering amplitudes. And we've seen many talks in this conference. I just listed a couple of them. There's like adjacent worldline methods that I apologize haven't listed here. But I want to focus on one particular setup, this Kossauer maybe O'Connell framework, this observable-based framework. We've already seen this also in I think in Ricardo's and maybe also Mao's talks. So what's the idea behind this KMOC framework? Well, the idea is that we can start from the quantum theory, and already in 78, Kovács and Thorne realized that any classical problem can in principle be solved quantum mechanically, and sometimes the quantum solution is easier than the classical one. And this is kind of the motivation or like the idea behind this KMRC framework. So as you know, in quantum mechanics, observables are encoded in quantum mechanics by some quantum Hermitian operators. And if you're interested in the change of some observable between the asymptotic future and the asymptotic past, we can take expectation values of this operator O. And since the asymptotic future states, the out states in the theory are related to the in states of the theory via time evolution operator, i.e. the S matrix, we can we can write this change in observables in terms of S matrix elements. So of course, for LIGO, we're not interested really in the quantum mechanical problem, but instead we have to take the classical limit. Either you can phrase it as h bar to 0, you can phrase it as Bohr's correspondence principle of large charges, large angular momentum masses, or the Compton wavelength of these particles are much smaller than this impact parameter where you scatter these two objects with respect to. Ultimately, that leads to the fact that we're in special kinematic regime of iconal scattering, where the energy, the center of mass energy, and the masses of these two macroscopic objects are much bigger than the momentum transfer between them. And after you do the setup, you can ask for certain specific observables that one might be interested in for classical physics. You can ask how much do the black holes get deflected in the scattering, or how much momentum, how much gravitational Bremsstrahlung is emitted during this collision process, or you could ask for the waveform directly. And again, because of effective field theory, like these black holes here are officially modeled by point particles. So with that, you can really, like once you do this in this KMRC framework, you can really see the analogy between these event shapes in gravity and the collider. So if you, for example, look at this radiate momentum, how much momentum is radiated in the scattering process, it's written in terms of scattering amplitudes weighted by a certain momentum thing. And so this is exactly like the weighted cross section that we've seen in the collider setting, where like the one-point function of the single energy correlator is also written as a differential cross section, or amplitude squared weighted by the energy. So with this, like the idea behind much of this program of using amplitudes tools for gravitational wave physics is we harness the progress in collider physics to make precision predictions for gravitational waves. So this is just a flash. We can actually you can do useful computations. This is from a paper with Julio from a couple of years ago. By now, this has been extended to higher orders in perturbation theory. And then there's there's other observables that one might discuss. Like there was a lot of recent progress on the waveform itself. One thing with classical physics is that due to some nice work by Donald O'Connell, Cristofoli, Gonzo, and others, is that we know in classical physics there is no quantum uncertainty. And what this means effectively is that higher point correlation functions factorize. So there's, so only the quantum mechanical uncertainty principle tells you that this higher point function has to factorize up to order h bar terms. So in the classical limit, the variance is negligible. So you don't have interesting multi-point correlators. So with this, we want to go to quantum gravity, where you can have non-trivial higher point correlators, and that's something we want to discuss. And so, as I said at the beginning, so these detector correlators, they're interesting asymptotic observables. We want to leverage field theory developments, these light ray operators, to explore the structure of gravity. And there already been some nice work in the classical limit by Ricardo and Andrzej Prokaka, who are both here, on the classical limit of these detector operators. So in order to study them, we need some data. So you look at the data mine, and the data mine is empty. So what you have to do is you have to generate your own data, which we did together with Murat and Ian. So we use the fancy tools from Amplitudes. We do a double copy, BCJ, to compute the leading order energy correlator in GR. In the situation, again, we don't want local operators. Instead we prepare the initial state by scattering of two massive scalar particles. And so once you go through the motion, the energy correlator is written in terms of the matrix element squared times some energy weighting factor in this alpha. You're left with a single integration variable alpha, which is basically the ratio of the energy scales of these things. And once you go through, you can get some nice cross-ratio variables in which you can express your result. So one thing I want to mention is that these results are relatively simple. So these are nice objects that have simple structures, simple theoretic structures. Here, the leading order, these are just given by weight one functions in terms of logarithms and some arctangents. There are some rational prefactors and so on. And once you have this limit, once you have the result, you can actually study its limits. So unlike gauge theory, these energy correlators, if you bring these two detectors together, because there's no collinear divergence in gravity, it's finite in this collinear limit. There's still a back-to-back singularity that's due to soft graviton radiation. So it would be interesting to try to resum this area, and you can do some nice plots here. Together with Kai-Yan also, we've done a similar analysis in supergravity, where we have data due to Svi Byrne and his collaborators to higher loops. So we have access to higher point correlation functions. So that's really nice. We are still exploring these things. What we're going to do next is we're trying to really extract OPE coefficients, try to find new detectors in these energy correlators, more general detectors in their normalization. Maybe one can try to study Hawking radiation processes and ultimately try to explore the space of asymptotic observables. In colliders, there's measurements across different collider platforms. So there's a lot of interesting physics to be studied. Okay, before I close, like really the final slide, I want to advertise if this type of physics is appealing to you, there's going to be a KITP program in 2027, which the application deadline is open. Oh, the deadline of application is October 5, 2025. So I encourage you to apply. Alexandre is also in the audience. If you have more questions, go talk to him. And with that, thanks again. Oh, so now it's actually, okay, so now our organizer is here. I think I want to take the opportunity to say thank you for this really wonderful conference, for making things go so smoothly, for like organizing a really, really great conference. And I think we should give Simon a huge, and all the other organizers a huge round of applause.